Imagine having a super smart assistant that can understand and respond to your every question and command. Sounds like science fiction, right? But with the help of large language models, this is now a reality. Large language models are artificial intelligence models that can learn and generate human like language, but to get them to perform at their best, they need to be trained and fine tuned. So, just like how a child learns to speak and understand language by listening and practicing, large language models needs to be pre-trained on vast amount of text data, fine-tuned for specific tasks and guided with carefully crafted prompts and instructions. So in this video, we will delve into the world of large language models and explore the 4 key concepts that make them tick. Pre-training, fine-tuning, prompt engineering and instruction tuning. We'll break them down into the simple, easy to understand language and show you how they work together to enable large language models to understand and respond to human language with unprecedented accuracy and fluency. So let's get started with understanding large language model, which is a type of artificial intelligence designed to process and understand human language. Here, pre-training is the process of training the large language model on massive amount of text data before fine-tuning it for specific tasks. The goal of pre-training is to teach the model the general patterns and structures of language so that it can learn to represent language in a way that is useful for a wide range of tasks. Pre-training is important because large language models have millions of parameters, so think of them as knob switches that needs to be adjusted to learn the complexity of language. Suppose we have to train a model from scratch on specific task. It would be like trying to find a needle in the haystack. The model will have to learn everything from the scratch and it can take a long time and might not give good results. So how does pre-training works? So first of all, the massive data set of text is collected from various sources such as books, articles, research papers and websites, and this data set is called pre-training corpus. Next, the text data is broken down into smaller units called tokens, which can be words, subwords or even characters. Then some of the tokens are randomly replaced with special token called mask. And this is done to create a masked language modeling task where the model has to predict the original token that was replaced. Then the large model architecture such as transformer is selected. And this architecture consists of multiple layers of neural networks that process the input text. Then the model is trained on the pre-training corpus using masked language modeling task where the model predicts the original token that was replaced and the error between the prediction and actual token is calculated. Then the model's parameters are adjusted to minimize the error using optimization algorithm such as stochastic gradient descent. And then it repeats the step of model architecture, training and optimization with the model seeing the pre-training corpus multiple times. Now the goal of pre-training involves language understanding where it teaches the model to understand the patterns and structures of language such as grammar, syntax and semantics. Then to learn the representation of language that can be used for a wide range of tasks such as text classification, sentiment analysis and language translation. And finally, to enable the model to transfer its knowledge to new tasks and dataset with minimal additional training. Now there are several pre-training objectives like masked language modeling, where it predicts the original token that was replaced with mask. The next sentence prediction means predict whether two sentences are adjacent to the original text. Token level classification means predicting the part of speech tag or the named entity recognition label for the given tokens. The benefits of pre-training involves improved performance, the transfer learning because the pre-trained models can be fine-tuned for new tasks and dataset with minimal additional training. Also, pre-training can reduce the amount of training data and computational resources required for specific tasks. Now, the challenges involves computational resources because pre-training requires large amount of computational resource and memory. Also, the quality of pre-training corpus can have significant impact on the performance of model. And finally, these pre-trained models can suffer from overfitting, especially when fine-tuned on smaller dataset. So in conclusion, this pre-training large language model is a crucial step in training artificial intelligence models that can understand and generate human language. By training a model on massive dataset and using techniques like masked language modeling, we can teach the model to represent language in a way that is useful for a wide range of tasks. Although there are certain challenges and limitations, but the benefits of improved performance, transfer learning and efficient training makes it a fundamental technique in natural language processing. Next comes the fine-tuning. Now this fine-tuning is the process of adjusting the pre-trained large language model to perform a specific task such as text classification, sentiment analysis or language translation. The goal of fine-tuning is to adapt a pre-trained model to the specific requirements of task while leveraging the knowledge and patterns learned during pre-training. So fine-tuning is important because pre-trained models are often too general and may not perform well on specific tasks. So pre-trained models are trained on large diverse dataset, but the task-specific data may be smaller and more specialized. So fine-tuning allows the model to learn the nuances of task-specific data and adapt to the specific requirements of the task. Now how does fine tuning works? So first of all, it will start with a pre-trained large language model, say BERT or ROBERTA, then collect the data set specific to tasks such as text classification or sentiment analysis. After this, pre-process the task specific data including tokenization, normalization, formatting, then add a task specific layer on the top of pre-trained model such as classification layer or regression layer. Then train the model on task specific data using pre-trained weights at starting point. Then the model is fine-tuned to minimize the loss function specific to the task. Also use an optimization algorithm such as stochastic gradient descent to adjust the model's parameter. And then tune hyperparameters such as learning rate, batch size and number of epochs to optimize the fine-tuning process. And there are several types of fine-tuning, like weight fine-tuning, where we fine-tune the weights of pre-trained models, layer fine-tuning, where we fine-tune specific layers of pre-trained models, adapter fine-tuning, where we add a small adapter layer on top of pre-trained model and fine-tune the adapter, prompt fine-tuning, where we fine-tune the model using specific prompt or input sequences. The benefits of fine-tuning involves improved performance, transfer learning because fine-tuning leverages the knowledge and patterns learned during pre-training, reduces the need for large amount of task-specific data, then efficient training and flexibility. Now there are certain challenges and limitations where overfitting means fine-tuning can suffer from overfitting, especially when the task-specific data set is small, then catastrophic forgetting, where the fine-tuning can cause the model to forget the knowledge learned during pre-training. Hyperparameter tuning means it requires careful hyperparameter tuning, which can be time-consuming and challenging. Also, the quality of task-specific data can affect the performance of fine-tuned models. So, we should always start with a good pre-trained model. Also, we should start with small learning rate and gradually increase it to avoid overfitting. We can monitor the model's performance on validation set and adjust the hyperparameters. Then we can use early stopping to prevent overfitting and reduce training time. Also, we should use regularization techniques such as dropout and weight decay to prevent overfitting. Now, there are certain fine-tuning techniques like BERT fine-tuning, where we fine-tune BERT models for specific tasks such as text classification and sentiment analysis. ROBERTA fine-tuning, where we fine-tune ROBERTA models for specific tasks such as language translation, question answering. Adapter fine-tuning, where we fine-tune adapter layers on top of pre-trained models such as BERT and ROBERTA. Prompt fine-tuning, where we fine-tune models using specific prompts or input sequences such as text classification and sentiment analysis. So this fine-tuning large language model is an important step in adapting pre-trained models to specific task and data sets. Although it requires careful hyperparameter tuning, data preparation and monitoring to prevent overfitting and catastrophic forgetting, but it helps in getting the better accuracies. Next comes prompt engineering, which is the process of designing and optimizing the input text or prompt that is used to interact with the language model such as chatbot or text generator. The goal of prompt engineering is to craft a prompt that elicits a specific response or output from the model, while also ensuring that the response is accurate, relevant and useful. Prompt engineering is important because the quality of prompt has a significant impact on the quality of response generated by language model. And this well-designed prompt can have improved accuracy because by providing clear and concise input, well-designed prompt will help the model understand the context, generate more accurate response. Also, it increases relevance and enhances the usability. There are several types of prompts, where open-ended prompts which allow the model to generate a response without any specific constraint or guidelines. Closed-ended prompts provide specific guidelines or constraints for the model to follow. Leading prompts provide a specific direction or tone for the model to follow. Neutral prompts provide a neutral or objective tone for the model to follow. Then prompt engineering techniques. So here first of all we need to clearly specify the task or the question that the model should answer. Then we should provide relevant context or background information to help the model understand the task or questions. Then we define the tone or style of the response, such as formal or informal. Then we use specific keywords or phrases to help the model understand the task or questions. We should avoid using ambiguous or unclear language that may confuse the model. Also, we can test the prompt and refine it based on the response generated by the models. And there are certain best practices for prompt engineering, where keep it simple, be specific and clear about what you want the model to do or answer. Use natural language and avoid jargons or technical terms that may be unfamiliar to the model. You should test the prompt and iterate it based on the response generated by the model, or also consider the limitations and biases when designing the prompts. There are certain challenges and limitations where the model may have bias or limitations that affect the response generated. Also, the model may not have a clear context or information to generate accurate response. The prompt may be ambiguous or unclear, leading to confusing or inaccurate response. Also, the model may overfit the prompt and generate a response that is too specific or tailored to the prompt. Its applications involves chatbots, text generation, language translation, and question answering. Now, the tools and the techniques for prompt engineering involves prompt templates, where using the prompt templates to help guide the design of prompts, using tools to analyze the prompt and identify areas for improvement, also using tools to understand how the model is interpreting the prompt and generating the response, and finally using human evaluation to test and refine the prompts. So this prompt engineering is a crucial step in designing and optimizing the input text used to interact with language models. However, it has certain challenges and limitations such as model bias, lack of context, and ambiguity, which must be considered while designing and optimizing prompt. Next comes instruction tuning, which is a technique used to fine-tune a pre-trained language model to perform a specific task by providing it with instructions or guidelines on how to complete the task. The goal of instruction tuning is to enable the model to understand the task requirements and generate high-quality outputs that meet the desired standards. Instruction fine-tuning is important because by providing clear instructions, developers can improve the model's performance on specific tasks. Also, instruction tuning enables models to adapt to new tasks and domains, making them more flexible and versatile. And finally, it can reduce the time and effort required to train a model because it leverages the pre-trained model's existing knowledge and capabilities. Now, how does it work? So, first of all, it should start with a pre-trained language model such as BERT or ROBERTA. Then define the task that the model needs to perform, such as text classification or question answering. Then create a set of instructions or guidelines that describe how to complete the task. These instructions can be in the form of text, such as classify the text as positive or negative, or answer the question based on the provided context. Then fine-tune the pre-trained model on the task-specific data using instructions as additional input. And this can be done using techniques such as supervised learning or reinforcement learning. Then evaluate the model's performance on the task using metrics such as accuracy or F1 score. And there are several types of instruction tuning, where explicit instruction tuning provides explicit instructions to the model such as classify the text as positive or negative. Implicit instruction fine-tuning provide implicit instructions such as through the use of priming or contextualization. Hybrid instruction fine-tuning combine explicit and implicit instruction fine-tuning, and its benefits involves improved model performance. Also, it enables models to adapt to new tasks and domains. It can reduce the time and effort required to train the model, and it can provide better insights into how the model is making predictions and decisions. Its challenges and limitations involves instruction quality that can significantly impact the model's performance. Also, the model's capability to understand and follow instructions can be limited. The model may overfit to the instruction and fail to generalize to the new task or domain. And finally, there is currently a lack of standardization in instruction tuning, making it challenging to compare and evaluate different approaches. Its applications involves natural language processing, where it can be used on tasks such as text classification, sentiment analysis, question answering. Also, it is used on computer vision models such as image classification and object detection. Finally, it is used to improve the performance of robotic system on tasks such as navigation and manipulation. And there are several tools and techniques for instruction fine-tuning, where the pre-trained language models such as BERT and ROBERTA can be used for instruction fine-tuning. Also, tools such as instruction generation frameworks and libraries can be used to create and optimize instructions. We can also use supervised learning and reinforcement learning. And we can use metrics such as accuracy and F1 score to evaluate the performance of models. So this instruction fine-tuning is a powerful technique for fine-tuning pre-trained models to perform specific tasks. Although it has certain challenges and limitations such as instruction quality, model capacity, and overfitting, which must be carefully considered when designing and implementing instruction tuning approaches. And that's a wrap. The journey of creating a highly effective large language models involves a combination of pre-training, fine-tuning, prompt engineering, and instruction tuning. By understanding how these four concepts work together, developers and researchers can unlock the full potential of large language models and enable them to generate human-like language that is accurate, relevant, and engaging. So whether you are building chatbot, language translator, or a text generator, mastering these concepts can help you create AI models that are not only intelligent but also intuitive and user-friendly. As the field of NLP continues to evolve, it's exciting to think about the possibilities that large language models can bring to various industries and applications. And we hope that this video has provided a solid foundation for exploring the fascinating world of large language models and their many applications. So thank you.